Just a moment, because there is a unstable Hello? Am I audible?
Yes, ma'am.
My screen is visible?
Some disturbance created, ma'am.
I mean, can you see my screen?
Ma'am, resound coming, ma'am.
Yeah. Hello? Is it
Good
okay now?
afternoon, ma'am.
Huh?
Hello?
Is it okay?
Okay, ma'am.
Are you able to hear?
Hello?
Hello?
Good afternoon, ma'am.
Good afternoon. Very good afternoon, everyone. Can you, hear me?
Yes, madam, we can hear you.
Screen is can you see the screen?
Yes, we can see the screen, but you didn't share anything, madam.
I have shared. That's why I'm
Yeah, you are audible, madam.
audible, but my screen is not visible, right? Yeah. Can you see that screen? Hello?
Yes, madam, we can see the screen.
Visible.
You can see the screen and you can, it is, I'm audible also, right?
Yeah, yeah.
Yes, madam.
Right.
Okay, let's start the lecture.
Yes, madam.
Thank you.
Yes, ma'am.
Yeah. Yeah. Today we are going to discuss about C13 and Nmr. Okay. And before discussing that, let us first understand the definition of spectroscopy. C13 and Nmr is also a part of a kind of spectroscopy which gives different type of information about the organic molecules. Actually, what is basically spectroscopy? Spectroscopy is the interaction of the matter with electromagnetic radiation, isn't it? So, electromagnetic radiation consists of different frequencies with different wavelengths, different frequencies and wavelengths. And different part of the electromagnetic radiation interacts with in different ways with the matter and gives very useful and different information. For example, in first year, you have studied IR spectroscopy, UV spectroscopy, and C13 and Nmr, proton NMR, etc. So different wavelengths of EMR. EMR means electromagnetic radiation interact with matter in different ways and give specific information, which is very useful in the structure elucidation. Okay. For example, interaction of IR part of electromagnetic radiation gives an idea about various functional groups present in the molecule. For example, you have carbonyl functional group in the molecule. So it will interact with a specific frequency, a specific wavelength of electromagnetic radiation, and it gives you IR spectrum. And from the signal, what you observe, you will be able to identify whether a carbonyl is present in the molecule or not. This you have studied in your first year. Similarly, NH2 group will have a specific frequency, IR frequency, and similar wavelength, frequency and wavelength. Okay. Similarly, OH also has different frequencies and wavelengths. So that way, by observing the signals, by observing the spectrum, you will be able to see what kind of functional groups are present in the structure in the molecule you are studying. Similarly, UV part of the electromagnetic radiation interacts with like matter and gives you some idea about the electronic excitations. So this you have studied in first year already, and proton NMR you have studied, that is NMR. It interacts with the NMR part of the electromagnetic radiation and results in nuclear excitations, nuclear excitation of magnetic nuclei. So here, so interaction with the NMR part of electromagnetic radiation gives information about the type of magnetic nuclei present and their chemical environment in the structure, isn't it? So proton NMR gives you information regarding the different types of protons that are present in the molecule. For example, this you have already studied in first year, so I just want to revise it. In proton NMR, what is the kind of information you get? From the number of signals, you get information regarding the type of different protons, what type of protons are present in the organic molecule, whether CH3 is present, whether it is attached to oxygen, whether it is attached to nitrogen, etc. Similarly, whether a CH2 group is present, whether aromatic protons are present in the molecule under consideration. So from the number of signals, you will get this type of information, a number of non-equal, I mean different protons, that is non-equivalent protons. Non-equivalent means magnetically non-equivalent, chemically non-equivalent type of protons. That information you will give you from the number, you will get from the number of signals from proton NMR. Chemical shifts. Chemical shifts, it is a shift in the position of the signal from the reference signal. That chemical shift values will give you the information regarding the chemical and magnetic environment of the different sets of protons present in the molecule. For example, you have para-methoxybenzaldehyde. Para-methoxybenzaldehyde. How many types of protons are there? OCH3 protons are there, aromatic protons are there, and CHO protons are there. So CHO has a different chemical shift. OCH3 protons have different chemical shift, and the aromatic protons ortho to OCH3 have got different chemical shift. Similarly, the aromatic protons ortho to CHO also will have different chemical shifts. So what I'm trying to say is, I'm just trying to revise from the chemical shifts. So you will get information regarding the chemical and magnetic environment of different sets of protons present in the molecule. Then another important feature of the NMR spectrum, proton NMR spectrum, is integration curves. So these integration curves will give you information regarding number of protons in each set. See, for example, para-methoxybenzaldehyde only you take. So in para-methoxybenzaldehyde, OCH3, you have 3 protons. And aromatic, you have 4 protons, and 4 protons also 2 different types of protons. 2 are ortho to OCH3, 2 are meta to OCH3, or ortho to CHO, and 1 CHO proton. So you will have integration curves 1:2, 2:2, 2:3. So that will give you the information regarding number of protons in each set. So OCH3, 3 protons, and ortho to OCH3, aromatic protons 2 protons, and meta to OCH3, that is ortho to CHO 2 protons. And CHO 1 proton. So they will have different chemical shifts, and integration under these signals also, I mean the ratio of these integration curves, the area under the signal, the integral area related to the number of protons in each set. And spin coupling. Another important feature that you have learned is spin-spin coupling. This gives information regarding the neighboring protons in proton NMR. So in proton NMR, 4 important aspects you will study. Number of signals will give you different non-equivalent protons in the molecule under consideration, and chemical shifts, it gives the information regarding the chemical and magnetic environment of different sets of protons present in the molecule. Integration curves gives you the ratio of the protons in each set. And spin-spin coupling gives you information regarding the number of protons number of neighboring protons in the molecule. Hello, you can hear me, no?
Yes,
I'm
ma'am.
trying to think. Hello?
Yes, ma'am.
Yes, ma'am.
Okay.
We are able to hear you.
Okay. Then, now, without going into details of proton NMR, because you have already come across that topic, we don't have much time. That's why I'm not going into details. You just revise because it is related to see that. I mean, the knowledge you have. I mean, you gained in proton NMR somehow will give you, more understanding about the other nuclear NMR spectra also. So it's better to have thorough knowledge of proton NMR also. Just refresh. Okay. So now let us come back. What is NMR? You know, NMR is the name itself suggests it is related to the nuclei of the different element atoms, magnetic nuclei that are present in the molecule. So what are the elements normally we come across in organic molecules? You have carbon, you have hydrogen, you have fluorine, you have phosphorus, and many elements you come across in organic molecules, but only certain elements which are magnetic, whose nuclei are magnetic, they only give rise to NMR spectrum. So nuclei of certain elements behave as tiny magnets because the nucleus of, for example, proton H1 or C13 or F19 or P31, they behave as tiny magnets. And when a magnet, you know, it's just a physical principle. When a magnet is placed in external magnetic field, though they will either it will be aligned with the applied field or opposite to the applied field. Actually, this is taken into consideration, especially this is the basis of NMR spectroscopy. Actually, nuclei, some elements of certain nuclei, nuclei of certain elements. What are the elements? For example, which we come across in organic molecules: carbon, hydrogen, fluorine, and phosphorus. They are magnetic. They behave as tiny magnets. So, in the presence of strong external magnetic field, these nuclear magnets align with the field or oppositely aligned with the field. That means they will orient themselves either with the field or opposite in orientation. Okay. So I come back to the principle. Actually, I'm just trying to say nuclear magnetic resonance spectroscopy is basically associated with the nuclei, with the nuclei of certain elements, which form the part of the which form organic structures, which are basic of all organic structures, like carbon, hydrogen, and fluorine, and P31, phosphorus. They behave as tiny magnets, and this magnetic moment is responsible for the nuclear levels excitation, and that in turn is going to interact with the the EMR part of the electromagnetic radiation. Because of that, they interact, they absorb energy from NMR part of the electromagnetic radiation, and get excited to higher energy states, and which is recorded in the form of the spectrum, which we are going to learn, which you have learned, but which you will be learning again a little bit later. Okay, but before that, I just want to, because we are starting with C13 NMR, let us try to understand the significance of C13 NMR. What is the significance? C13 NMR, as you know, I mean, it consists of the nuclei of carbon. It is related to the spectroscopy related to carbon, which is magnetic. So carbon 13 is magnetic, and it is that is why we call it C13 and Nmr. So why it is so significant and so important? Because as you all know, organic chemists, because carbon is the backbone. Carbon is the center of interest in organic chemistry. Without carbon, actually no organic compound exists. So it's actually carbon is very important. It actually forms the backbone of organic molecules. And okay, it forms. So what? Because hydrogen also is there in organic molecules, and proton NMR spectroscopy is enough for structural elucidation. You may think like that, but all the time proton NMR will not be giving you the required information about the molecular structure. Why? Because there are many natural products which contain more carbons than hydrogens. So if just proton NMR will not be able to give you the sufficient information required for the structural elucidation, because natural products will be complex molecules. They will have more carbons sometimes and less number of hydrogens. And from the chemical shifts, integration curves, spin coupling patterns of in proton NMR, you may not be able to arrive at the full information, full structural information just from proton NMR. In such cases, C13 NMR will come to your rescue in structural elucidation. So many natural products contain more carbons than hydrogens, and since we are observing carbons directly from C13 NMR, it's going to be very important. And just proton NMR, that's what is written there in the slide. Just proton NMR is not enough to elucidate the structures of such compounds, such complex molecules where you have less number of protons and more number of carbons, number one, and where protons chemical shifts are very closely spaced, and where there is so much overlapping, you will not be able to see any signal, any specific signals related to particular set of protons, especially if the molecule is very complex. That is the reason why in such cases the proton NMR will be complex and very difficult to interpret. So in such cases C13 NMR will be helpful. And carbon 13 NMR can give information regarding the bonding state of carbons also directly. So here you can say whether sp3 carbons are there, sp2 carbons are there, sp carbons are there, or quaternary carbons are there. Though proton NMR sometimes gives, but there tetra substituted carbon, since it will not have any hydrogen attached to it, you will not be getting any information from proton NMR. So when you compare proton NMR and C13 NMR, C13 NMR will give you more information because it is actually observing the backbone of the structure, backbone which is the carbon structure. Carbon is a backbone, and which is it will give you more information than proton NMR. And because carbon and carbon bonding states, like hybridization states also you can know. So from that you will be able to assign which type of structure is present in the unknown molecule, and even you can confirm the known molecule structure also by taking C13 NMR. So and that is a significance. And bonding states of carbon explains the physical properties, reactivity, etc. You know pretty well, sp3 carbons have some kind of reactivity, sp2 have different kind of reactivity, and in that also sp2 aromatic carbons will have specific reactivity patterns. So you will be, and even sp hybridized carbon will have different set of different type of reactivities. So from that, while designing the new reactions and while understanding the physical and chemical properties of new organic molecules, this will be helpful. Okay, so you can directly check the carbon backbone structure. You can understand the hybridization patterns, and it will give you more information, especially in case of complex molecules. Now, just spectroscopy. Let us see what is the basic principle involved in this spectroscopy. I was referring to magnetic nucleus. Carbon carbon is the very important basic element of organic molecules, but all carbon atoms that are present in organic molecules are not magnetic because they have two different isotopes, C12 and C13. C12 is not magnetic, is non-magnetic. Why? Yeah. What kind of nuclei are magnetic? What kind of nuclei are magnetic? The nuclei whose I is 0, spin number is positive. I mean, which is not 0, it should be positive. It can be half, it can be 1, it can be 3 by 2, etc. But it should not be 0. When I value is 0, it is non-magnetic. When I is positive, it is magnetic. And here, carbon isotope, the most abundant carbon isotope, carbon 12, is non-magnetic. Why? Because its I value is 0. Therefore, C12 cannot be absorbed by NMR techniques because the basis for NMR is magnetic nucleus. Since carbon 12 is not magnetic, it cannot be absorbed by NMR techniques. And carbon 13, that's why all this we refer to, not just carbon NMR. Sometimes, for simplicity purpose, we refer carbon NMR, but it is basically not just carbon NMR, means it is carbon 13 NMR only, not carbon 12 NMR, because carbon 12 will not give you any NMR spectrum. Carbon 13, whereas it is magnetic. Why? Because its I value is 1 by 2. But the problem with carbon 13 is its abundance is only 1.1%, and the rest all, it is carbon 12. 98.9 is carbon 12. 1.1% is carbon 13. So that small percent of carbon 13 nuclei are responsible for giving NMR spectrum. Okay. And another one, the magnetic moment, because when they are magnetic, they will have a specific magnetic moment. That magnetic moment of carbon is about 1/4 of proton. So it's less than proton, and its sensitivity is low. See, carbon 13 abundance is very less, and carbon 13 magnetic moment is also less than 1/4 of proton. It is less than proton, about 1/4 of proton. That is the reason why overall sensitivity of carbon 13 is about 1/6000 as compared to proton. So that is also one of the reasons we used to require before sophistication. We used to require more sample for recording C13 NMR, but less sample for proton NMR. Okay, since the sensitivity is low, continuous wave mode technique. This also you have studied for proton NMR. It's a kind of a recording technique. Two modes are there: continuous wave mode and PFT, pulsed Fourier transformation mode. It's method of recording NMR spectra. So similarly, here also you have CW and PFT modes, but since the sensitivity is low, carbon 13 NMR spectroscopy is not normally used. I mean, CW technique is not used. Hello.
Ma'am, screen is not changing. Only it's for me or for all?
For you?
Stop from starting to up to here, only one screen is there.
Screen is not changing.
Hello? Any problem?
From the starting part to introduction,
Hello?
only introduction sheet, first sheet only display, ma'am, not changing the sheets.
Huh? Screen is not visible?
Visible,
Madam,
ma'am.
screen is
Actually,
visible.
only introduction sheet.
Okay. You are not able to see other slides?
Yes, ma'am.
Now, can you see?
Only introduction sheet. Now display, ma'am.
Is it okay now?
Okay, ma'am.
I just revised them. So this is what I have mentioned. Interaction NMR part of electromagnetic radiation gives information about the type of magnetic nuclei present in the molecule and their chemical environment and the structure. Okay, so proton NMR, I told you number of signals give you information regarding the type of different protons, non-equivalent protons, and chemical shifts gives the information regarding the position, the position of the chemical shift will give you the information regarding the chemical and magnetic environment of different sets of protons present in the molecule. For example, OCH3 and CHO. So OCH3 methoxy protons will have some particular chemical shift, and CHO proton will have a particular chemical shift. So from that, we will understand whether OCH3 protons are there in the molecule, whether an aldehyde proton is there in the molecule. Similarly, aromatic protons also will have different chemical shifts. This is just a revision about proton NMR only. I've already told you. Since you have not seen the screen, I'm just repeating it. That chemical shift information will give you different types of chemical and magnetic environment of different sets of protons present in the molecule. And integration curves will give you information regarding the number of protons in each set. For example, para methoxy benzaldehyde, methoxy 3 protons, aromatic protons 4. In that also two protons are different, and CHO1. So 1:2, 2:2, 2:3. So that ratio will be observed in proton NMR. And spin coupling, it gives you information regarding the neighboring protons. Okay. So this is the information you get from proton NMR. I told you orally. I think you could not see the screen. That's why I'm repeating. And next, you see, I told you that different nuclei of certain elements behave as tiny magnets: carbon, hydrogen, fluorine, and phosphorus. So they behave as magnets. So when they are placed in strong external magnetic field, they align with the field or opposite to the field, especially if I is equal to half. With all these nuclei have got I is equal to half. I'll come back to it in the principle later. This is what I told you. Then significance also, I've told you, carbon is the center of interest in organic chemistry because it is the backbone of all organic molecules. And carbon 13 is very important because many natural products contain more carbons than hydrogens, and just proton NMR is not enough to illustrate the structures of such compounds. Okay. If there is any problem, you please, let me know, because I need not repeat. Okay. Hello.
No problem, ma'am. It's okay.
Yeah. Now, this is the significance I was referring to. Carbon is the center of interest in organic chemistry. It is the backbone, and many natural products contain more carbons. They are very complex. They have very complex structures with less number of hydrogens and more number of carbons. So in such cases, carbon 13 will be carbon 13 NMR will be very important for structural elucidation. And moreover, even protons, even if the number is less, they may be overlapping because due to the closer chemical shift range, protons, different sets of protons that are present in the molecule may overlap, and you will not be able to see a highly resolved spectrum, and which is very difficult to interpret, which may be very difficult to interpret, and that is the reason why carbon 13 NMR is very important. Okay, and carbon 13 NMR will give you information regarding the bonding states. That is hybridized states also. The single bond is there, double carbon, doubly bonded carbons are there, or triply bonded carbons are there, or even double bond also. Whether you have aromatic carbons, whether you have aldehyde carbons, like that, you will be able to know. So that is the significance. You get more information than proton NMR. Though proton NMR is very, very helpful in structural elucidation, sometimes it is very difficult because of various reasons, because of the structure complexities. So this structure complexities, when you are facing problem, if you take C13 NMR, it will be very useful. That is the significance. Now, this is where I think, yeah. Now, the most abundant carbon isotope is C12, but it is non-magnetic. I told you in the beginning itself, only magnetic nuclei will give, NMR spectrum. Because they will have, they will place themselves in different orientations. That means two nuclear energy levels are formed. That means there will be difference in energy states. from the lower energy and upper energy states, and they can interact with EMR and get excited. This is same as proton in Nmr, and yeah, principle we will discuss. So the most actually what I'm trying to refer to or explain you is carbon 13 NMR refers to magnetic carbon. So magnetic carbon nucleus. So which is magnetic nucleus of carbon? Carbon 13 is the magnetic nucleus. Carbon 12 is not magnetic. Why? Because only for a nucleus, for if its spin number I is equal to more than 0, that is positive, then only it is magnetic. But for carbon 12, it is I is equal to 0, therefore it is non-magnetic. And whereas carbon 13, the I value is half. So, but I value is half, therefore it is magnetic. Carbon 12 is non-magnetic because I is equal to 0. Carbon 13 is magnetic. Why? Because I value is half. But the problem here is its abundance is only 1.1%. I told you carbon 12 is more abundant, carbon 13 is less abundant. And another important feature of carbon 13 is its magnetic moment. It has magnetic moment, no doubt, but its magnetic moment is less than proton, about 1/4 of proton. Therefore, its sensitivity is very, very low. And so its magnetic moment is less than proton, and its abundance also is less, very less, whereas proton is high. It is not 1.1, it's more. So because you have only other two less abundant isotopes for proton, proton H1 is more abundant. That's why there is no abundance problem with proton, magnetic protons, whereas here the abundance problem will be there. That is the reason why the overall sensitivity of carbon 13 is about 1/6,000 as compared to proton. So the sensitivity is very less, and that will make carbon 13, a little bit difficult to record, and that's the reason why the techniques that are used, both techniques, see the continuous wave mode, PFT mode, both can be used for proton NMR, though we are not using CW technique very often, even in proton NMR. Here carbon 13 also, it is normally not used because continuous wave technique will take days together to record one C13 NMR spectrum. So that we will discuss more about different types of, recording this you must have come across in proton NMR already. So it may not be there here, but you have two different recording techniques. For your information, I'm telling you, carbon is continuous wave mode and PFT mode, and continuous wave mode takes a longer time. PFT mode method takes less time, and here PFT method is used to record the spectra. Okay, carbon. So what is the summary of present discussion? Carbon 13 is magnetic and it gives rise to NMR spectrum. Why? Because when a magnetic nucleus is placed in external magnetic field, this is what same as PMR. I'm just showing you. When a charged particle, it can be positive or it can be negative. When a charged particle is placed in presence of applied magnetic field, it creates a magnetic field that thus the nucleus can be considered to be a tiny bar magnet. This is tiny actually this is external magnetic field, and the spinning charge also creates a magnetic field. So that is the magnetic field of the particular nucleus under consideration. So this is the external magnetic field. B0 is the external magnetic field, and this is the spinning nucleus. Here we are just showing, we are able to say only one element nucleus. This is the nuclear spin of only one element, but an organic molecules contain many elements. Carbon, just one carbon will not be there. No, many carbons will be there, and just as a representative case, and just showing you one carbon atom whose nucleus is magnetic. So that is spinning. It is spinning around its own axis like this. It's tiny bar magnet. So a spinning magnet is placed in presence of applied magnetic field. Now it will have a characteristic motion which we call precessional motion. That is, it will rotate around the axis of the applied magnetic field. So this is applied magnetic field, And the spinning magnetic field, it is rotating around its own axis, and it is also rotating around the axis of the applied magnetic field. So here two are there. One is spinning, the other one is precision. One is spinning, same as proton NMR. If you remember, this is this is any magnetic nucleus, you can say. In proton NMR, it is proton. In C13 NMR, it is carbon-13. Okay, the carbon-13 is spinning around its own axis, and it is rotating around the axis of the applied magnetic field. Okay, this is called axis. This is axis of precision, and this is precisional motion, and it has got a frequency called precisional frequency. When precisional frequency comes to resonance with the applied frequency, then absorption occurs. Now, this spinning nucleus can have two different orientations. One is in line with the applied magnetic field. Okay, one is like this, in the same direction, and the other one opposite in line. That means it will be precise. They're just opposite the oppositely oriented. The same picture you just visualize, it will be oppositely precise. So two nuclear energy states are created. One is low energy state, the other one is higher energy state. So that energy difference is very small. That energy difference is very small, and it falls in the NMR part of the electromagnetic radiation. Okay, that actually that energy difference is related to the magnetic moment, and it is a characteristic of the nucleus under consideration, magnetic nucleus under consideration. Okay, so when two energy states are created, there is a possibility of absorption. So absorption of what? Absorption of radio frequency. Radio frequency from where? From the electromagnetic radiation which we are going to supply in regarding the NMR spectrum. That is radio frequency. So in regarding NMR spectrum, you have a magnetic nucleus, you have applied magnetic field, you also have radio frequency which will supply the energy to to excite the nuclei from low energy state to higher energy state. So that absorption is recorded in the form of NMR spectrum. So that is the reason why it nuclear magnetic resonance. Okay, when another thing, when this absorption occurs, when the precisional frequency matches with the radio frequency that we apply, then resonance occurs. Then exchange of energy takes place, and nuclei will get excited from low energy state to higher energy state. Hope I am actually, and again repeating, it is same as proton NMR, which you have studied in first year. Okay, any magnetic nucleus, when placed in applied magnetic field, it will have a characteristic motion called precisional motion. And this will have any motion. This will have a particular frequency which we call precisional frequency. When precisional frequency comes to resonance with the radio frequency which we apply, then nuclear energy absorption occurs, and the nuclei from the low energy state to get excited to higher energy state, and that absorption is recorded in the form of NMR spectrum. This is the most simplified version of the principle of proton C13 NMR. For that matter, any NMR. Okay, any NMR. Only thing is here precisional frequencies differ, magnetic moments differ. They are characteristic of different nuclei. Proton have a particular precision frequency. C13 have got a different precision frequency, and F19 has got a different precision frequency, and therefore they come to resonance at different radio frequencies. Actually, that is the reason why when you are recording proton NMR, you will not see carbon signals. When you are recording C13 NMR, you will not see proton signals, because if we are taking organic molecule, in the same organic molecule, we have carbon, we have hydrogens, we have fluorine, we have phosphorus also, depending on the structure. You may have a doubt when we are recording proton NMR, why we can't see C13 spectrum, because their magnetic moments are different, their precision frequencies are different, and they will not come to resonance with the radio frequency in the proton range. That is the reason why we will not be able to observe carbon-13 signals in proton and Nmr. Similarly, when you are recording C13 and Nmr, you will not be able to observe proton signals in proton and Nmr spectrum. So that is actually one of the very important thing you should understand and remember also. And so what is that you understand? Principle is same as proton and Nmr. Like proton, carbon-13 is also magnetic. That magnetic nucleus spins around its own axis. It also precesses around the axis of the applied magnetic field, and it will have a characteristic frequency called precessional frequency. And when that precessional frequency comes to resonance with the applied radio frequency, then absorption occurs, and that absorption is recorded in the form of Nmr. So I'm just giving you some important dispersional frequencies of carbon. Actually, applied. There is some printing mistake. Actually, it is a table, and this is the applied magnetic field. This is the precessional frequencies. See, at 1.4 Tesla applied magnetic field, carbon-13 will have precessional frequency 15 Hertz. Do you remember what is the precessional frequency of proton? It is 90 megahertz, not hertz, it is megahertz. That also a printing mistake. 115 megahertz. So at 1.4 Tesla, carbon-13 has got precessional frequency 15 megahertz, whereas proton has got almost 90, 15 force, roughly about 4 times, 90 megahertz. 1.9 Tesla, so 13 has got 20 megahertz precessional frequency, and whereas proton has got 80. Okay, this is 60, this is 60, this is 80, and 2.3 Tesla, it is around 100. So 100 megahertz precessional frequency it has got. So we call it a spectrum. I mean, it will be more resolved than this. Okay, so I'm just giving you the precessional frequencies of carbon, and similarly, at same applied magnetic field, proton will have different precessional frequencies, and fluorine will have different set of precessional frequencies. Phosphorus will have different, and if for that matter, any magnetic nucleus has got different precessional frequencies. So when we use that corresponding radio frequency, we will be able to record different spectra, that particular, like here carbon-13 spectra we can record, and when you use proton precessional frequency, proton precessional frequencies range in the EMR region, radio frequency region, we observe proton and Nmr spectrum, and similarly proton F19 and P31 and Nmr spectrum. Okay. This is the difference, and you can observe. See, I told you carbon's magnetic moment is around 1/4 of proton. Similarly, precessional frequencies are also directly proportional to the magnetic moment. They are also less than the precessional frequencies of proton. At the same applied magnetic field, proton has got roughly 4 times precessional frequency than carbon. So this is one of the, I mean, it's a difficult to like instrumental problem, especially while recording C13. Why C13 is difficult to record? I mean, the sensitivity of C13 is less. Why proton and Nmr is easy? Why? Because it is a sensitivity problem. Sensitivity is less for C13. Abundance is less, and magnetic moment is less. This is the basic Nmr equation, Nmr equation. It is also same as proton and Nmr, same. I am not going into details of it. This equation is basic Nmr equation. This is the frequency of precession of the nuclear magnetic moment is directly proportional to the product of the magnetic field strength, that is applied field, and the gyromagnetic ratio. This gyromagnetic ratio is specific for specific nuclei. For proton, it is different. Carbon-13 it is different, and other magnetic nucleus it is different. That is the reason why precessional frequencies also are different. Okay. Now that is about the principle of C13 and Nmr. Briefly, I revised the significance and of CMR. Actually, here the difficulties. I mean, slide is missing. C13, the difficulties slide is missing here. The advantages I have shown you. I have shown you. Yeah, advantages of C13 and Nmr. C13 Nmr, did we, yeah, this we missed. Advantages of C13 significance we have seen, and but advantages we have not discussed. What are the advantages of C13 and Nmr? The advantage is the range of chemical shift is wide. It is roughly between 0 and 240 ppm. Whereas for proton NMR, it is just about 0 to normally 0 to 10, sometimes 0 to 12, and sometimes 0 to 16. That's all, maximum 18 ppm. Whereas the C13 chemical shifts are widely, like their range is wide. Normal range itself is 0 to 240. That means the signals, C13 signals are widely distributed in this range. So definitely there will not be overlapping. The range of chemical shift differences among carbon atoms is more as compared to PMR, because all the organic molecules, protons will observe in the very narrow range between 0 and 12 in most of the cases, and 14 and 16 very specific cases, but normally 0 to 12 only, 0 to 10 only actually, to be precise. So in that only all protons of almost all the complex or simple molecules, they fall in that region only. That will be, there is a possibility of overlapping in proton signals, of overlapping of proton signals in proton NMR, whereas this overlapping is not, I mean, normally it does not happen because of the chemical shifts range. It's quite wide. So signals are quietly, signals are nicely separated. Okay, overlapping is minimum. And here another advantage of C13 NMR is even non-protonic functional groups you can observe, like nitriles, carbonyl groups, carbonyl of carboxylic acid, carbonyl of ester, and hexasubstituted benzenes, di-substituted alkyne carbons, tetra-substituted alkene carbons. So all these groups you cannot observe in proton NMR because they do not have attached proton. Whereas in C13, since we are directly observing carbon, you can observe these groups also. This is one of the very important advantages of C13 NMR. So suppose, for example, you have hexa-substituted benzene. If you take proton NMR, you will not be able to see aromatic protons at all. You will not be able to see aromatic protons at all. So that means aromatic, you may miss that maybe aromatic ring is not there in the molecule. Whereas when you observe C13 NMR, you can see hexa-substituted carbons of that benzene carbons also you can see. So from that chemical shift, you will be able to know whether benzene, I mean, aromatic region is present, aromatic carbons are present in the molecule or not. This is another very important advantage in structural elucidation. And as I told you, it's possible to identify the carbon backbone structure in mixture can be easily identified because of the wider chemical shift range. Okay. Advantages and disadvantages. Disadvantages slide is missing. Disadvantages are, as I already told you, lesser magnetic movement, abundance is very less, sensitivity is very less. That is the reason why for recording carbon 13 NMR, you require more sample and a little bit sophisticated instrumentation technique. So that is the disadvantage. And we have seen this principle, we have seen, and the precision frequency I discussed, and Nmr Equation. Now, let us come to, I mean, you have different types of C13 and Nmr spectra also. And from different kind of C13 types of C13 and Nmr spectra, we get specific information, we get useful information. So mainly 4 types of C13 and Nmr spectra are there, normally recorded. One is undecoupled spectra, the other one, second one broadband decoupled or proton decoupled spectra, third one off resonance decoupled spectra, and selective proton decoupled spectra. So you have these 4 types of spectra while recording C13 and Nmr. Each will give you different information that we are going to discuss. Let us first discuss about undecoupled spectra. So what is this undecoupled spectra? The name itself suggests what in this type of spectra, all couplings between carbon and hydrogen and other magnetic nuclei are observed. Another disadvantage with carbon. Actually, it is advantage also in specific cases, and but disadvantages in while recording. Why? Because carbon undergoes coupling with almost, I mean, it undergoes coupling with other magnetic nuclei. What are the other magnetic nuclei that are present in the molecule? Hydrogen. Hydrogen definitely may be present. Other carbons, I mean, other carbon 13s and fluorine, P31, etc., etc. Not only that, it will couple with the directly attached protons and protons 2 bonds away, 3 bonds away. So long range couplings are also possible. So carbon undergoes extensive coupling with not only attached hydrogens and which are hydrogen, but it also couples with which are 2 or 3 bonds away and even longer range coupling sometimes. So that gives number of signals, more number of signals, which may result in overlapping of the signals, which may result in complex spectra. So this results in very complex spectra, even for simple molecules. Therefore, very difficult to interpret. Therefore, this is not normally used because I told you carbon 13 Nmr is used, especially when proton Nmr is not sufficient to give you the required structure information. So here, undecoupled spectra will give you complex spectra even for simple molecules. I'm showing you with an example here. See, just a simple spectrum. Nobody will take carbon 13 or proton for a simple molecule such as propanol. Just proton Nmr is enough for this. But still, if you want to take, say, just as an example, I'm showing you, even proton and carbon 13 Nmr of such simple molecule as propyl alcohol will also be complex. Why I'm telling you, suppose when you are observing this carbon, the carbon that is attached to hydroxy group, this can couple with attached hydrogen, that is J1 coupling, we call it J1 coupling. It can also couple with the hydrogen present on the second carbon, that is alpha carbon. It can also couple with the hydrogen on the third carbon, that is beta carbon. I mean, the second carbon from the carbon under consideration. But when you take in this carbon also into consideration, is the third carbon. So it will couple with the directly attached hydrogen. It will couple with this hydrogen, J2 coupling. It will also couple with this hydrogen, J3 coupling. This is J3 coupling. J1 coupling, J2 coupling, J3 coupling. All are possible. And if you remember the equation, that is the number of signals it can give from, again, we'll go back to proton Nmr only because most of this your basic formula and all you've learned in proton Nmr, but I just want to revise. Suppose if you remember the number of signals that can be obtained from a coupling pattern, it is given by a simple equation: 2 NaI plus 1 into 2 NBI plus 1 into 2 NCI plus 1, and so on, so forth. So Na means number of A type of other magnetic nuclei. Number of NB means B is the number of B type of magnetic nuclei. C is the number of C type of magnetic protons. That means suppose if a particular set of protons are coupling with A, B, C, only we will take only two types of protons into consideration. Suppose if a set of protons are coupling with A type of protons and with a B type of protons, it will give you multiplet. It will give you number of signals will be equal to 2 NaI plus 1 into 2 NBI plus 1. Then suppose if Na, the number of protons in A type of protons is 2, or 1, let us say only 1, to Na means 1, to NaI plus 1. So you just calculate, it will give you more signals in proton Nmr also. So see here, this we'll calculate for this only. J1, J2, J3 couplings are possible. So theoretically, 36 lines are possible. For what? For this CH2OH carbon. How? See, it has got A type of protons, A type of magnetic nuclei, 2 NaI plus 1. 2 into 2 NaI into 2 into 2 into half plus 1. So that will be 3, right? 2 into 2 Na. 2 into Na is 2. 2 into 2, 2 Na. I is half for hydrogen into half. So 1, 2 gets cancelled. 2 plus 1, it will be 3. Then into 2 Na NBI. NB is this. Nb is 2, Nb is equal to 2 hydrogens. Nc is equal to 3. You just calculate, put these figures and just multiply and see 2Na plus 1 into 2Nba plus 1 into 2Nca plus 1. It will come to 36 lines. So just one carbon of simple molecule of propanol will give you 36 lines. Imagine again the similar, this carbon also will give 36 times. Then it will be here to NAI, to NBI, to NCI. So if you just incorporate these figures, you will get those many number of signals lines. For this carbon also, for this 36, 36, 36, it will need so many lines in the spectrum and very difficult to interpret. That is the reason why. And since we are not going to take C13 and Nmr of simple molecules, we are not going to use undecoupled spectra often. Okay, where we can use it only where number of other magnetic nuclei or number of hydrogens are less in the molecule, so that the number of signals will be less. Only in such cases we use, but normal cases we will not use undecoupled spectra. Why? Because it will give you more number of signals based on that formula, 2Na plus 1 into 2Nba plus 1 into 2Nca plus 1. So based on that, if you calculate, you will get these many lines, and you calculate and tell me. Suppose we will do more exercises also later after completion of the lecture. After completion of the topic. Okay. Next. That is undecoupled spectrum. So this is normally not used because it is a complex spectrum. Yeah, this continues. See, it has got J1, J2, J3 couplings are possible. Theoretically, 36 lines are possible in CH2 carbon in one propanol. That is, one propanol. So since all the spin-spin couplings are observed, these spectra are called undecoupled spectra. So all the couplings are observed. No coupling is removed. No protons are decoupled. Undecoupled means to simplify the spectra, we decouple some of the protons to simplify the spectra. But here no protons are decoupled, so it is undecoupled, and it will give you complex spectra. Okay, the undecoupled spectra of principal molecules are complex due to overlapping of multiplets. This is what I told you, from different carbons, because different carbons will like undergo coupling with attached hydrogens, hydrogens with 2 bonds away, hydrogens which are 3 bonds away, etc. And one more disadvantage is C13H couplings are normally larger as compared to proton couplings. Proton couplings fall in the range between 8 and maximum 12, like that. But whereas here 125 to almost 300 coupling constant will be there. So which will make even more complex, which will make the spectrum even more complex for simple molecules. Now, next is broadband decoupled spectra. What is this broadband decoupled spectra? The name itself suggests here something is being decoupled. What is being decoupled here? All the hydrogens, because the hydrogens that are present in organic molecules are giving rise to what? Complexity. Different, because number of lines are more, they are giving rise to complex spectra. Suppose if you can remove the couplings due to all the hydrogens, then definitely the spectrum will be simplified. So in broadband decoupled spectra, the protons the protons are decoupled. All the protons that are present in the molecule are decoupled. So how the coupling constant between carbon directly attached hydrogens ranges from this one. Since this results in overlapping, proton decoupled spectra are used. Here I told you, because of the coupling constant and also the number of signals, you get a complex spectrum even for simple molecules in undecoupled spectra. So since we require a simplified spectra to interpret the spectrum, to understand the structure, we need to simplify it. So how we can simplify? By removing the coupling between carbon and hydrogens. So that is possible by decoupling. Decoupling what? Decoupling of all the hydrogens that are present in the given molecule. So how it is done? We use a broadband. What is this broadband? Broadband consists of radio frequencies, all the radio frequencies, which are related to proton frequency range. Proton frequency range in the organic molecules. So you take a broadband which consists of proton frequencies and irradiate the sample. In that case, what happens? All the protons undergo faster excitation and relaxation. Therefore, the nearby carbons will not be able to see the protons in different energy states. So, which is the basis of spin-spin coupling. Actually, but again refer to your proton spin-spin coupling basic principle. The basis is carbon can see protons in different energy states, both in lower energy state and higher energy state. Attached protons and protons that are little bit nearer. So it can see different energy states, which results in coupling, which results in the different frequencies, and that is why it gives different signals. But here, what we are doing, we are using a broadband of radio frequency, which consists of all the radio frequencies, which corresponds to the radio frequencies of all the protons, all the possible protons that may be present in the molecule. So all the protons that are present in the organic molecule, the given molecule, are excited. They undergo faster excitation and faster relaxation, and carbon can see only the average spin state of those protons. So therefore, it will not undergo coupling. It will not undergo coupling. So only carbon signal will be observed. Here, a broadband to decouple all the hydrogens present in the molecule, and another radio frequency corresponding to carbon crystal frequency, that is to record the carbon signals. So two frequencies are used. One is broadband, which corresponds to the proton frequency, and the other one radio frequency, which corresponds to the carbon crystal frequency. So we are using carbon crystal frequency to observe the directly carbons which are not able to see protons in different spin states. That is why they will not couple. So any non-equivalent carbon will give only singlet signal, only one line. So since this results in okay, in this technique, simultaneous irradiation of all the proton resonances is carried out. That is what I am referring to. Broadband means it is the proton resonance frequency. The band consisting of different a band consists of radio frequencies of corresponding all proton resonances. Okay, it is carried out with a broadband generator, and while observing the carbon frequencies. So carbon frequencies untouched, and carbon spectrum is being recorded, but only the coupling of, the proton NMR, protons present in the organic molecule are irradiated with the corresponding proton frequencies. This is broadband. Okay. So what happens when it is done? It results in, see, this is what I told you. This results in flipping of two spin states of proton faster, and the attached carbons can see only the average of the possible spin combinations. Therefore, it will not only average signal. It will give you not the low. For example, when you suppose, for example, I'll tell you one example. It can give you doublet, because one hydrogen, it can see in two spin states, one in lower energy state, the other in higher energy state. So it can give you two lines. So one hydrogen attached to n+1 rule, it will give you two lines. We call that doublet, isn't it? SEH can give you doublet. But here, what is happening? Since there is faster flipping of energy, spin states of proton, carbon will be able to see only the average average spin orientation of protons. That is why carbon is observed as just singlet only. Okay, this results in decoupling of all the protons, and because of this NOE, actually this nuclear overhauser effect, the signal intensity also increases. This NOE also you have studied in proton NMR, but when I mean, different protons which are undergoing faster excitation, which are being irradiated, are nearby carbon, and that carbon can give up its energy, which will increase the signal intensity. So therefore, because of NV effect in broadband decoupled spectra, intensity of the signal, carbon signal, also increases, which will make the interpretation, identification of different carbons present in the molecule very easy. So from this, we are using two radio frequencies, two sets of radio frequencies. One to observe carbon signals, other one to decouple all the protons present in the given molecule. So with the result, what happens? All the protons are decoupled, and carbon is observed as a singlet. Okay. The number of signals. So now, what is the information you get from this? Signal intensity increases, and carbon, all non-equivalent carbons appear as singlets. So what is that? You are going to get with example. We'll see. Then this spectrum. The number of signals gives the number of different types of carbons present in the molecule. Because you know pretty well, from the number of proton signals in proton Nmr, what is that you identify? Suppose if you have two types of signals are present in the Nmr spectrum, proton Nmr spectrum, what is that you understand? You have two types of non-equivalent protons in the molecule. For example, ethanol, if you take CH3, CH2, OH, isn't it? Proton Nmr, if you refer to CH3 protons are there, CH2 protons are there, OH is there. So CH3 one signal it will give you, CH2 another signal it will give you, and OH another signal. So overall for ethanol, how many signals you get? 3 signals you get. So 3 different types of protons. And suppose if you have diethyl ether, how many signals you will get in proton Nmr? 2 signals. What are they? CH3 protons signal one, CH2 protons another signal. So that what is that you understand from that? You have 2 types of protons are there present in the given molecule. And suppose the same ethanol or diethyl ether, carbon 13, take. How many different carbons are there? Again, 2 types, CH3 carbon and CH2 carbon. So you will observe 2 signals. The number of signals gives the number of different types of carbons present in the molecule. This is what you get from broadband decoupled spectrum. And the number of signals is equal to number of non-equivalent carbons. Definitely, equivalent carbons will not give you, different signals. Ethyl ether. You have 2 CH3 carbons are there, 2 CH2 carbons are there. But those CH3 carbons are equivalent. Those 2 CH2 carbons are equivalent. So you don't get 4 signals. How many signals you get? You get only 2 signals. Why? Because only 2 non-equivalent carbons are there. And another is C13 and Nmr signals are not integrated because this is the experimental technique is different, unlike a proton Nmr. So in proton Nmr, you can observe integral curves because the area under the integration is directly proportional to the number of protons present in the given signal, in the given set. So that is the reason why their integration curves are very important. But C13 Nmr, you don't get integration curves because it will not give you the right information. So they are not integrated. The peak intensity is not proportional to the number of absorbing carbons because of this reason. Okay, because NOE effect is there. NOE effect also increases peak intensity, and so because the intensity is not just related to the number of carbons, it is also related to NOE effect and neighboring hydrogens, etc. That is the reason why integration curves are not given in C13 and Nmr as in the case of proton and Nmr. So I'm just showing you some examples. Broadband decoupled spectrum of dimethyl ether. See how many carbons are there? Here 2 carbons are there, no doubt. But how many non-equivalent carbons are there? This CH2, this CH2, both are same. Both are same, is it not? So that is why they give only 1 signal. Chloroethane. How many different carbons are there? 1 CH3 and other one CH2. 2 different carbons are there. So it gives you 2 signals. Methyl acetate. So methyl acetate. Here how many carbons are there? Can anybody tell? Say no. 1 CH3 carbon and the one OCH3 carbon and carbonyl carbon. See, if you observe the proton NMR of this methyl estate, how many signals you would see? Only this and this. Only two types of proton signals you will see. Because this carbonyl carbon of ester is not attached to any proton, you will not observe in the proton NMR spectrum. Whereas in C13 NMR, you can observe this. CH3 signal you can see, CO you can see, and CH3 you can see. So you can see three signals. Okay. Yeah. Some more examples here I am giving you. See, ethane. Ethane, how many non-equivalent carbons are there? Only one, because both CH3s are same. So both carbons are equal, therefore only one signal is observed. One carbon signal is observed in broadband decoupled spectrum. Okay, propane you see. How many non-equivalent carbons are there? Two. This CH3, CH3 both are same, and this CH2 is different. So you will get two signals. Two non-equivalent carbons, therefore two signals. Again, N-butane. How many? This CH3, this CH3 are same. This CH2, this CH2 are same, and middle one is different. So three signals, three non-equivalent carbons are there, therefore three signals. And methyl, ethyl, ethyl. So how many? 1, 2, 3. Three non-equivalent carbons, therefore three signals. Benzene, if you observe, 6 carbons are there, no doubt, but all are equivalent, right? So therefore only one signal for benzene. And next, broadband decoupled spectra of this one, ethyl, phenyl, ethyl. Here you see ethyl, phenyl, ethyl. How many are there? 1, 2 in ipsocarbon. Then one is which is attached to oxygen, and these two are same. These two are same. These two. This one is same. So 1, 2 and ipsocarbon 3, 2 orthocarbons 4, and 2 metacarbons 5, and this one paracarbon 6. So overall 6 non-equivalent carbons are there, therefore 6 signals are obtained. And diethyl phthalate. Here you see there is symmetry here. See, so many carbons are there. 1, 2, 3, 4, 5. Actually 1, 2, 3, 4, and 6, 10, and 4, 14. Total 14 carbons are there. But you don't observe 14 signals. Why? Because there is symmetry here. 1, 2, 3. And these all the 4 are same. Actually, this is CH2, this is CH2 are same. This ipsocarbon are same. This carbonyl carbon, this carbonyl carbon are same. And all aromatic carbons, and all 4 aromatic carbons are same, because all these 4 are ortho to the same group. So there is symmetry, mirror image. Okay, 1, 2, 3, 4, 5. So only 5 non-equivalent carbons are there. Therefore, 5 signals are observed in broadband decoupled spectra. Okay, so that's it. So we have seen undecoupled spectra. We have seen broadband decoupled spectra, and next one is off resonance decoupled spectra. You know, actually, if you observe off resonance decoupled, the spectra what we studied. Undecoupled spectra, even for simple molecules, the spectra are complex because they give more number of lines. And proton decoupled spectra, all the coupling information is lost. You get only the signals due to carbons. So, but some of the information is lost. So that is the reason why we have another kind of spectra of resonance decoupled spectra. This gives you more information. See, the disadvantage of proton decoupled spectra is the coupling information is lost. Proton coupled spectra give complex spectra. So that is the reason why we have different kind of recording. This is of resonance decoupled spectra. Here, coupling information is not completely lost, but the spectrum is simplified. How it is simplified? Here, the coupling due to attached hydrogens is observed. The attached, carbon attached hydrogens is observed, and coupling due to other hydrogens, that is 2 bonds away, 3 bonds away, or 4 bonds away, longer range couplings are not observed. How it is achieved? It is also achieved by irradiating the sample at a frequency, frequency which is closer to the frequency range of all the protons, but not the exact range. In the proton decoupled spectra, we use complete broadband, which is corresponding to the proton radio frequencies. Here we use slightly off resonance of the proton range, slightly. Normally 1000 to 2000 hertz of field of normal proton frequencies, or about 2000 to 3000 down field of proton frequencies of TMS is used. In between, proton signals are observed. Proton Nmr spectrum, but we are using slightly upfield than TMS and slightly downfield than TMS as a decoupling frequency. So that's why we call it off resonance. It's not the resonance frequency of protons. It is not the resonance frequency of protons. It is slightly off resonance frequency of the protons. So with the result, what happens? Coupling information is not completely lost. Only the coupling between carbon and directly attached hydrogens is observed. But that is also residual coupling only, not full coupling is observed. It's only residual coupling due to attached hydrogens is observed. So that makes the coupling multiplets easier to identify, because the coupling constant is reduced. We just see doublets, triplets, quartets as we see in proton Nmr. Simply we can see very easy. So from this, what is the advantage? You can get you can get the information regarding directly attached protons, but all other long range proton couplings is lost. So the spectrum is simplified. Okay, so here we use off resonance frequency as the decoupler frequency. So that will simplify the spectrum and also retain some of the coupling information. The coupling, residual coupling we call it. It's not the true coupling. It is a residual coupling that is given by the equation J residual is equal to 2 pi J delta nu by gamma B2. So here J is a true coupling constant, and see that the difference between the resonance frequency of the protons of interest and decoupler frequency is slightly off resonance, I said, no? So it is based on the instrumentation that is set. Okay, gyromagnetic ratio of the protons, and B2 is the strength of the rotating magnetic field generated by the decoupler frequency, which we are using. The decoupler frequency also generates the secondary magnetic field, rotating magnetic field, that is known by B2. So this is the equation that is used to calculate J residual coupling. Okay. Next. Now, this residual coupling is observed, but what is the information? Especially, we are more concerned about this information. What is the information that we are going to get from this spectra? See, the residual coupling is proportional to the J1CH coupling. If the J1CH, the original true coupling is more, residual coupling also is more. Okay, and the power of the decoupling and the distance at which the decoupling. This is the instrumental parameters. So it is based on that. But the information what we get is this based on it's given by the N+1 rule. All CH3 carbons present in the molecule appear as quartets. All CH2 carbons in the molecule appear as triplets at their respective chemical shift values, and all CH carbons appear as doublets, and all quaternary carbons appear as singlets. So just by looking at these patterns, we will know how many CH3 carbons are there, how many CH2 carbons are there, how many CHs, methane carbons are there, how many quaternary carbons are there in the molecule. Same, it's like similar to proton Nmr, the ratios of these triplets, quartets, and is similar. 1:2:1, 1:3:1, etc. But it's not very informative, because we are not going to take into consideration. It's roughly like that only, like what we observe in proton and Nmr. So I'm just giving you the examples, and after discussing these examples, because we have wasted more time in the beginning, so that's why I'm taking another 5 minutes time. Hope you don't mind. See, examples of SFO are the ethyl acetate. Half resonance decoupled C13 Nmr spectrum of ethyl acetate gives 4 signals. See, ethyl acetate 1, 2, 3, and 4. So here CH3, one carbon is attached to 3 protons. So N+1 rule, 3+1, quartet. CH3 is it appears as quartet. And CH2, one carbon is attached to 2 hydrogens. So N+1 is 3. N is 2 plus 1, 3. That is triplet. And here it's not attached to any hydrogen, therefore singlet. And this again attached to 3 hydrogens, so quartet. So 2 quartets it will give, 1 triplet and 1 singlet. Just by looking at the pattern and molecular formula, you will be able to assign the structure for simple molecules. So always remember, all CH3s appear as quartets, all CH2s appear as triplets, and all quaternary, I mean the carbons which are not attached to hydrogen appear as appear as a singlet. Ethyl benzoates, same thing I am showing you. See, 1, 2, 3, 4, 5, 6, 7 carbons are there. So 7 signals you will get. CH3, since it is attached to 3 protons, you will get a quartet. CH2, 2 protons, it is attached, so you get a triplet. And here, this is not attached to any proton. This singlet, and this is a singlet is because it is not attached to proton. This is attached to 1 hydrogen, so doublet, doublet, doublet. So from the pattern of these multiplicities, you will be able to check the you'll be able to know how many types of carbons. Like even CH3 means sp3 hybridized carbon. In that way also you can know. Okay. Some more examples. Here you see ethyl methyl ketone. How many? 1, 2, 3, 4. 4 carbons. 1 quartet, CH3 quartet, CH2 triplet, and this is the quartet. And here you see this is ethyl protonate. Ethyl protonate also CH3 quartet. How many? 1, 2, 3, 4, 5, 6 signals. CH3 quartet, CH2 quartet, C double bond of ester singlet, and CH of this double bond, this one doublet, this is doublet, and this is quartet. Half resonance decoupled spectrum of ethyl protonate shows 6 signals and 2 quartets, 1 triplet, 2 doublets, and 1 singlet. Similarly, para-ethoxybenzaldehyde, if you see 1, 2, 3, 4, 5, 6, 7. 7 carbons are there, 7 non-equivalent carbons are there, therefore 7 signals, and it will give you quartet, CH3 quartet, CH2 triplet, this no hydrogen attached, it's a singlet, and this attached to 1 hydrogen doublet, this attached to 1 hydrogen doublet. This is, I mean, again, no hydrogen singlet, and CHO also is attached to 1 hydrogen doublet. So para-ethoxybenzaldehyde, that kind of pattern is observed. Okay. Yeah, it's time for 38. I think it's time to wind up. Right? Hello? Hello?
Yes, ma'am.
Yes, ma'am.
Yeah, it was okay, no?
Okay,
Shall I
ma'am.
stop? Yeah. Hello?
Okay, ma'am. Okay, ma'am.
Yeah, I'm closing it here. And in the next session, next Saturday, I'll be discussing the selective proton decoupling and also about chemical shifts in the given like molecules in C13 and Nmr. Okay. If you have any like, okay, we'll discuss it later. Anyway, thank you for your attention, and I am leaving. Okay.
Thank you, ma'am.
Yeah, you're welcome. And actually, yeah, we'll discuss it later. We'll see you in the next class. That is next Saturday, I think. Okay. Bye.
Okay, thank you, ma'am.
రూపాయలు సంపాదించుకోవాలి. ఏమన్నాడు ఇప్పుడు?
వస్తాను మీరు వచ్చిండ్రు అన్నాను నేను నల్గొండ. నేను బ్యాంక్ కాగితం పేపర్ రాష్ట్రం చెప్తాను సార్. కాగితం తీసుకున్న బ్యాంక్ లో వచ్చిన నేను ఎక్కడ మాట్లాడతాను.
శ్యామ్ సార్, శ్యామ్ సార్, హలో శ్యామ్ సార్,
ఆన్లైన్